We're now going to look at turning points or stationary points on a curve. A turning point is where a curve changes direction. So I have drawn a curve that goes through 3 points A, B and C. A, B and C are all turning points. If you take a look at point A, the curve is on the way down as it approaches A, but then immediately after A, it's on the way up. So the curve changes direction at A. Likewise, it also changes direction at B because just before it hits B, it's on the way up, but after B, it's on the way down. And likewise, as the curve approaches C, it's on the way up almost. I know it's going down, but you almost think it's about to turn up. But then it swings away and goes back down. So C is also a turning point. So a turning point is where a curve changes direction. Now these 3 turning points have special names. A is called a local minimum turning point, and that is because in the region around A, the value of y on the curve has its smallest value. So if you're just looking at the region around A and nowhere else, A is a minimum turning point because y has its smallest value at A in that region. B is called a maximum turning point because in the region immediately surrounding B, y would have its maximum value in that region, its highest value, its maximum value. C is called a point of inflection, which we're now going to talk about. So, a point of inflection, this occurs when the actual gradient of the tangent has the same sign immediately before and after it. So what I've done is I've drawn 2 curves and there is a point of inflection in each curve. And the reason these are points of inflection is because if you draw a tangent to the curve immediately before the point of inflection and you draw a tangent to the curve immediately after the point of inflection, the actual gradient of those, the sign of the actual gradient, will be exactly the same. Now be careful, I didn't say the actual gradient will be the same, the sign of the actual gradient will be the same. So you notice that the signs of these gradients here will be both positive because the tangents are sloping up, so they have a positive gradient. Likewise, over here we have a point of inflection because again, if you draw a tangent to the curve immediately before the point and immediately after the point, you'll notice that the sign of the actual gradient of the tangent before and after the point are exactly the same. These 2 tangents slope down, so their gradients will be negative. So the actual gradients of these tangents will be negative and therefore both the same. So that's how you know these are points of inflection. Final point. You'll notice that at every turning point, the tangent is a horizontal line and the tangent has an actual gradient of 0. So if we go back to the top, so at A, if I were to draw a tangent to the curve at A, it would be a horizontal line, likewise at B, and likewise at C. And the gradient of any horizontal line is always 0. So that's the next important bit to remember. So at any turning point, the tangent is a horizontal line, and the actual gradient of the tangent is 0 at those points. Now, what we're going to look at is how to find the coordinates of a turning point on a curve and their nature. So as we've just said, at any turning point, the actual gradient of the tangent is 0. So we set the general gradient dy by dx equal to the actual gradient, which is 0. So it's summarized there. So at any turning point, you set the general gradient equal to the actual gradient. In other words, dy by dx is equal to 0. You then solve that equation to get the x coordinates of the turning point, or turning points. You then sub the x coordinates of the turning points into the curve to get the y coordinates of the turning points. You then have to get the nature of the turning points. In other words, is the turning point a maximum, a local maximum? Is it a local minimum? or is it a point of inflection? The only way to determine that is you need to get the second derivative, d2y by dx squared, and you sub the x coordinates off the turning point into the second derivative. Now, if the second derivative is bigger than 0, then that will give you a minimum turning point. So that will be what the turning point looks like. If the second derivative turns out to be less than 0, then it's going to be a maximum turning point. If the second derivative is equal to 0, well, that's bad news because it's inconclusive. In other words, that's telling you it could be a maximum or a minimum or a point of inflection. So what do you actually do if the second derivative is 0? Well, you have to calculate the actual gradient immediately before and after the turning point to determine its nature. And we'll talk more about that when we do example 2 very shortly.